Hello again. This is Math 2245 coming to you from the College of DuPage. And the title of this lecture is Midterm Spring 22 Solutions. As always, please be an attentive learner while watching this video. Problem number 1 asks you to solve the following system of equations for the variable x4. So you had 4 equations and 4 unknowns. The easiest way to solve for a single variable is to use Cramer's rule. And so Cramer's rule involves computing a couple of determinants. This is the determinant where the right-hand side is replacing the x4 column, and this is the determinant of the coefficient matrix. And so we're taking the quotient for x4 to be, it is minus 48 over minus 58, and there's a factor of 2 in there, so x4 is 24 over 29. Number 2 asks you what is the null space of the transformation defined by this matrix. So to find the null space, we have to take this matrix times a column vector A, B, C, D and set it equal to the 0 vector and solve. Now you can see because of this 0 column here, A is not involved in the calculation at all, so A is a free variable in the first setting, and so we can have A times 1, 0, 0, 0. But what happens is the other will give you 3 equations and 3 unknowns, and so we get this, this, and this when we multiply the matrices, setting them equal to 0. Now the last equation tells us that 4c is equal to minus 2d, so c is equal to minus 1/2 d. And we can take that value and substitute it into the second equation for C and D, and we can find out that D has to equal minus, B has to equal minus D. And we really need to validate, or should validate, that that works in the second equation, but it also does. So you see everything is really a multiple of D. So the solution to this is going to be A times 1, 0, 0, 0 plus D times 0, and then this is going to be negative 1, negative 1/2, and 1, and so the null space is the span of this vector and this vector. The question 3 is the column vector 8, 28, 14 in the range space of the transformation defined by this matrix, and to explain your answer completely. Well, it will be if I can take a vector AB, set it equal to this, and solve for what AB must be. So I set up the equation and I solve it, and I find out that yes, the vector 3, 2 will be mapped to 8, 28, 14, and so that means that yes, it is in the range space, and in fact we've proven it because the vector 3, 2 takes us there. Problem number 4, you would perform an LEU factorization for A, and here is A, and the most straightforward process for this is to start with augmented matrices, where you have A over here. This is A, the 3 by 4 matrix, and you start with a 3 by 3 identity here, and you perform elementary row operations to put the matrix A into row echelon form. And when you do that, when you complete that, you will have an upper triangular matrix here by definition. And with the row operations happening here, you also have a lower triangular matrix. So if you perform that on this one, this is what you will get. And so here was the matrix that you started with, and this is the L, lower triangular matrix, and this is the upper triangular matrix that will give that to you. So that's the solution to the problem. Problem number 5, I asked that you calculate the determinant of this. It should be a straightforward calculation, and you get negative x plus 1. Number 6, the question asks you to find a 3 by 3 matrix that will replace the second row of a given 3 by 3 matrix with minus 3 times the first row added to the second row. Well, that means you have to have minus 3 and 1 here. But then you will also want to replace the third row of that same matrix with minus 5 times the first row added to the third, and that would be this. And so, but we said a single matrix, it could be the product of the two elementary matrices, but this is the single matrix that will do both of these things. In problem 7, you were to find the inverse of the matrix. Again, the process that we do is we can start with I, the identity matrix over here, and start with A. Then we can perform elementary row operations, turning this A into the identity matrix. And if we do that for across both I and A, we will end up with A inverse here. And if you do that, the inverse of this matrix is surprisingly all integers. And this is the answer that you should have gotten at the end of the problem. This is number 8, and so this we were to decompose the vector 3 minus 1 comma 6 into the sum of orthogonal vectors, one of which is parallel to 8, 7, and 3. And so we will get the scalar coefficient here for 8, 7, 3 by taking the dot product divided by the norm of this 8, 7, 3, and we'll take this coefficient times 873, and that is a unit vector in the direction of 873. And then we will subtract that from this vector, and we will have a component that is perpendicular. So what we find is that the vectors are this one plus this one, and you can check to see that these two do sum to our original vector, which I did here. And you can also check that their dot product is equal to 0, which means they're perpendicular one with another. And so the solution then is you want to have this vector as one of the vectors, and this is the other vector. Problem number 9 was a proof. I reminded you of the definition of symmetric matrix is one that's equal to its transpose. And I also invented or told you about skew symmetric was defined to be it's the negative of its transpose. So the thing you were asked to prove is that every matrix can be written as a sum of a symmetric and a skew symmetric matrix. So what we can do is we can observe that A is equal to A minus A transpose, and plus A plus A transpose, and actually that should be divided by 2, so you should say, well, 1/2 of that, because those will cancel out. But you see these scalar multiples of the 1/2 is going to, that's not going to be a problem. They still will be skew symmetric and symmetric. And so all we really have to do is show that this is skew symmetric and this is symmetric. So if I take the transpose of this, A plus A transpose transpose is A transpose plus A transpose transpose. That's A transpose plus, and that's going to just be A, because the transpose is equal to the double transpose gets you back to the matrix itself. Okay, so that is symmetric. Similarly, if we take A minus A transpose whole transpose, that will be equal to A transpose minus A transpose transpose, which is the negative of A minus A transpose. So you see, if we put a 1/2 in front of each one of these matrices, then we will have written A as the sum of a symmetric and a skew symmetric matrix, and so we've proven the assertion. Number 10, suppose that A is an n by n matrix, another proof, and that A squared plus 3A is equal to I. Prove that A is invertible. Well, we can factor out A out of the left side, or we could factor A out on the right side. So if we take A times this matrix, or this matrix times A, we will get the identity. So by definition, A is invertible, and in fact, this is what the inverse is. Number 11, we were to prove that A and B commute if B is invertible and if A is B inverse AB. This, by the way, is something more general called the commutator, and this is actually an important thing in higher algebra courses. So anyway, let's just do the proof of this, though. So suppose B is invertible and A is equal to this. You want to show A and B commute. That is, we want to show BA is equal to AB, and this sequence of operations will ensure that. So B times A is B times this business, because this is what A was. But then we can associate B with B inverse. That gives an identity times AB, and we just get AB. So that is the proof of the assertion. The last problem was number 12. We were to say if A is an n by n invertible matrix and A inverse is equal to A, we want to prove that the determinant of A is equal to either plus or minus 1. Okay, so suppose that A is equal to A inverse. Then A times A is the same thing as an A times A inverse is equal to I. So that means the determinant here of A times A, or A squared, is equal to the determinant of I, which is 1. But the determinant of A times A is the determinant of A times the determinant of A. That's a theorem that we proved. So that is equal to 1. So that means this is the determinant of A whole squared as a number is equal to 1. That means x squared is equal to 1, and so the determinant of A must either be plus or minus 1. So that's how you should have proved this one. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. We all can and should strive to make a difference. God bless you all.